We are going to be doing two different example problems in this video. Hopefully it'll be decently short and sweet, but you never know with these practice problems. Sometimes they go a little bit longer than you would expect. So we're going to be doing 8.2 and 8.3 from your book. 8.2 says, in photosynthesis, plants convert carbon dioxide and water into glucose according to this reaction. So we have 6 CO2 plus 6 water goes to 6 oxygens and glucose, which is C6H12O6. So that is the reaction that's taking place. The question asks, how many grams of glucose can be synthesized from 58.5 grams of CO2, assuming that there is more than enough water present to react with all the CO2. So if we have 58.5 grams of CO2, how much glucose can we make? So we're going to do the exact same process we did in the last video. We're just going to go from the mass of one thing to the mass of something else using this three-step process. So our first step is the molar mass of CO2, which is, let me add those together real quick. Wait, that was 44.1, wasn't it? Yeah, 44.1. Because we had 12.01 plus 16 times 2. Yeah, from the last video. I should remember that. So we have 44.01 grams of CO2 for every 1 mole of CO2. So that was this first step here, the first mole mass to mole conversion. Now we're going to do the moles of one thing to moles of something else conversion, and we do that using the balanced chemical equation, which in this case is a 6-to-1 ratio. So pretty big difference there. We have 6 moles of CO2 for every 1 mole of, and I'm just going to put glue instead of writing out the whole thing, so glucose. Now again, I'm putting the moles of CO2 in the denominator here because I need it to cancel out with the moles of CO2 in the numerator over here. So then the last conversion factor here is converting out of moles of glucose and into the mass of glucose. So I need the molar mass to do that, which means I need to add all of these up. So I have 6 carbons, which are 12.01 each. So 6 times 12.01 plus 12 times 1.01 for the hydrogens, plus 6 times 16 for the oxygens. So if you add all those together, you get for every mole of glucose 180.18 grams of glucose. And so if I check my units here, grams of CO2 cancel, moles of CO2 cancel, moles of glucose cancel, leaving me with grams of glucose, and I have a whole bunch of stuff to type in here. So, okay, 58.5 divided by 44.01 divided by 6 divided by 180, or sorry, not divided, oopsie, times 180.18. That gives me 39.9 grams of glucose. So nearly 40 grams of glucose. Way to go, little plant. Making its own sugar. It doesn't need to drink any Mountain Dew to get some sugar. It can just suck it out of the air and the sunshine. And technically the water too, I guess. So, way to go, little plant. Not only did you make your own sugar, but you made some oxygen for us to breathe, too. Much appreciated. Alright, so the next practice problem is 8.3. And it says, one of the components of acid rain is nitric acid, which forms when NO2, a pollutant, reacts with oxygen and rainwater according to this simplified reaction. And this is a much simplified reaction, but it works for our purposes. So we have 4NO2. That reacts with oxygen gas and water to make 4, oops, I should write that correctly. 4HNO3. My little bit of dyslexia was coming through there. I was trying to write the N before the H. All right, so the question asks, assuming that there is more than enough oxygen and water, how much nitric acid in kilograms forms from 1.5 times 10 to the third kilograms of NO2 pollutant. Now, this one is going to be a little bit more intense than the previous one, but only because we're dealing with bigger numbers, for one thing. We have a really large mass, and we're starting and ending with a different mass. We've essentially added on an extra step to the beginning and the end here. So instead of starting in grams, we're going to, oops, go back there. We're going to start in kilograms and go to grams, and then go from grams here to kilograms in our answer. So we're adding on an extra step on both ends, but that extra step is pretty easy and straightforward. It's just a grams to kilogram or kilogram to gram conversion, and that's just a 1,000 to 1 conversion. So let's go ahead and do that. So the value that we had here was 1.5 times 10 to the third kilograms of NO2. I'm going to go ahead and convert that to grams first, because I need it in grams to convert it to moles, because the molar mass is in grams per mole. So for every 1 kilogram, I have 1,000 grams. Now once I have that done, I can use the molar mass of NO2. So the molar mass of NO2, let me see, nitrogen is 14.01, oxygen is 16, and I have 2 of them, so that is going to give me 46.01 grams of NO2 for every 1 mole of NO2. So right now, I'm here. I started at kilograms, and I converted into grams. That was my first conversion factor. And then I used the molar mass to convert to moles here. So now, I'm going to use the balanced chemical equation to figure out how many moles of, what was it I was trying to find? Nitric acid, yes. How many moles of nitric acid I can produce given a certain amount of NO2. And in this case, this ratio is essentially a 1-to-1. So for every 4 NO2, I'm going to have 4 nitric acids. So this ratio isn't actually going to change the value numerically, but it is going to change the units, and so we don't want to get rid of it. We can't just leave it out. So then the last couple steps here are converting back into grams. So for every 1 mole of HNO3, I will have, I'm going to add this up real quick, so I have 1.01 for the hydrogen, plus 14.01 for the nitrogen, plus 3 times 16 for the oxygen. So the molar mass of nitric acid is 63.02 grams. So then the last one here, I need to convert back out of grams and into kilograms again, because the problem did specifically ask for the answer in kilograms. Whew. Okay, that looks busy. If we check our units here, kilograms cancel, grams cancel, moles of NO2 cancel, moles of nitric acid cancels, and the grams of nitric acid cancel, leaving us with kilograms. And so if we do all of that math, we have 1.5 times 10 to the third times 1,000 divided by 46.01 times 4 divided by 4, just leave that out, times 63.02 divided by 1,000. And what we get is 2.05 times 10 to the third kilograms of nitric acid. Oops, sorry, I kind of crossed out my 3 there. But a lot of nitric acid is produced. Now, you might have also noticed that the 1,000 here and the 1,000 down here canceled each other out. I would still encourage you to put those in, not necessarily into your calculator, but still go ahead and include them when you're working through the calculation, because sometimes the question won't specifically ask for the answer to be in kilograms. And so if you just start in kilograms, but then you end in grams, you can't leave that conversion out. So go ahead and make sure that you write everything down, and then if you notice, oh, look at that, I have 1,000 in the numerator and I have 1,000 in the denominator. Well, then at that point you could leave them both out, because they're just canceling each other out. All right, we'll call it there for this video. In the next one, we will talk about limiting reactants, where maybe you don't have enough of something. Maybe something is going to run out before everything else does. So we'll talk about that in our next video.